Dear students, after studying this module, you shall be able to know what is molecular ion, metastable ion and the base peak. You will also learn how to calculate molecular formula from molecular mass. You will learn to identify molecular ion peak and base peak in a mass spectrum. You will learn in detail about the nitrogen rule and also analyze the presence of chlorine and bromine atoms from the isotope peaks. Now let us begin with the introduction of this topic. A vertical bar graph generally depicts mass spectrum. Each bar represents an ion with a specific mass to charge ratio, also represented as m/z, and the height of the bar depicts the relative abundance of the ion. If the molecule gets devoid of an electron in the process of ionization, then a molecular ion is observed that yields its molecular weight, and it is indicated with M+ sign in the spectrum. As Z is more often than +1, m/z actually amounts up to the mass of the individual ions. Now let us show an example to you what I mean by saying all this. For example, the mass spectrum of dopamine, which is a neurotransmitter, has a base peak at 153, which is equal to its mass. Then you can say more often Z is equal to 1. Now you can see the structure of dopamine, and seeing its molecular weight at 153, you can see the m/z peak, which is representing actually the molecular mass of dopamine. Now let us come to some important definitions. First of all, I would like to tell you what is a radical cation. In the process of ionization of a molecule, the species so formed is known as a radical cation and is generally depicted as M+ with a dot. Dot represents the radical and plus sign represents that it is a cation. What is now a molecular ion or a parent ion? They are both the same. The former species mentioned above, that is the radical cation, is also known as molecular ion or the parent ion. So now you know that there are three definitions or three names for the same molecule, that is molecular ion, parent ion and radical cation are one and the same things. The mass of M+ dot, that is radical cation, represents the molecular weight of the molecule which is under scrutiny or whose mass is to be determined. Now radical cation M+ dot should be the highest m/z in the spectrum, apart from weak satellite peaks that result from other isotopes. Now let us come to the definition of base peak. Students, the ion formed most abundantly during the process of ionization gives rise to the tallest peak in the mass spectrum, which is also known as the base peak. All other peak intensities are obtained and they appear relative to the base peak as a percentage. Now what are fragment ions? The next definition. When a molecule loses a valence electron, further bonds are broken and new species are formed, and they are called fragment ions. Now let us come to the study of index of hydrogen deficiency, or also known as degree of unsaturation, or also known as double bond equivalents. The index of hydrogen deficiency is the number of pi bonds and or rings in a molecule. One double bond equivalent, that is 1 dBe, also known as degree of unsaturation, abbreviated as Du, is 1 pi bond or 1 ring. A triple bond counts as 2 dBe. Having 4 dBe shows the possibility of a benzene ring. Benzene has 3 pi bonds plus 1 ring. The dBe thus accounts for 4, and 4 or more indicates that the compound is likely to have more than one aromatic ring or aromatic ring and a double bond. Now how do you calculate dBe or double bond equivalents? The formula for DBE is, you start with a square bracket and then in the curly bracket you have 2a plus 2, curly bracket closed, minus curly bracket b minus d, another bracket closed, then you close the square bracket, whole of it you divide by 2. Now here students, A is the number of carbon atoms, B is hydrogen or monovalent atoms, D is nitrogen. Now let us come to another important definition of metastable ions. The ions appearing at an m by z ratio depends on its mass as well as the mass of the original ion from which it is formed. This ion is called the metastable ion. These peaks are usually broad and appear at non-integral values of m by z, that is molecular ion peak. The presence of a metastable ion peak links two peaks together, or you can show it as m1 plus gives rise to m2 plus a fragment. So m star is equal to m2 whole square divided by 1. Now here students, m star is the apparent mass of the metastable ion which is formed, m1 is the mass of the original ion, and m2 is the new mass of the fragment ion which is formed. Now consider here as an example C5H9 plus, it has a m by z value of 69, and C3H5 plus having an m by z value of 41 plus C2H4 having a value of m by z 28. Now calculated m star will be 41 square divided by 69, which equals to 24.36. So observed mass of the metastable ion will be 24.4 when you round it off. Now metastable ions arise because of fragmentation after the ion has left the ionization chamber. The kinetic energy of such M2 plus ions is smaller than when it would have been formed in the ionization chamber and accelerated there only, and it will be detected at a lower m by z value than expected. Now students, let us learn about the very important nitrogen rule. Most of the hydrocarbons and other compounds which contain carbon, hydrogen and oxygen atoms often contain a molecular ion with an even mass. A molecular ion which is odd indicates that a particular compound has an odd number of nitrogen atoms. Now let us just quote nitrogen rule in a particular example. So the effect of n atoms on the mass of the molecular ion in a mass spectrum is called the nitrogen rule. According to the nitrogen rule, a compound that contains an odd number of atoms has an odd molecular ion. A compound that contains an even number of nitrogen atoms, now even, I mean even here is even 0. 0 is considered as an even number over here, has an even molecular ion. Let us picture this effect. Consider ethylamine, which has the molecular formula CH3, CH2, NH2. This substance has one nitrogen atom and its mass is odd according to the nitrogen rule, and its value is 45. Whereas if you consider ethylene diamine, NH2 whole twice, CH2 whole twice, has two nitrogen atoms and its mass is even number, that is 60. So this is what the nitrogen rule basically states. Let us take another example. The 4-methyl-3-pentene 2-one has no nitrogen, so the mass of the molecular ion m by z is an even number, that is 98. Now you can see this in this figure. Most of the fragment ions have odd numbered masses and therefore are even electron cations. Now if you see diethyl methylamine, another one nitrogen containing compound, and its molecular mass will be odd. So m by z value for diethyl methylamine is 87, which is an odd number. Now a majority of the fragment ions have even numbered masses and are even electron nitrogen cations. Now I hope you can appreciate the nitrogen rule with these examples. Let us now come to the study of rule of 13. Now students, the rule of 13 is a useful method for determining the possible molecular formula of a compound from its molecular mass. In the rule of 13, first a base formula is generated which consists of only hydrogen and carbon atoms. Now this base formula is calculated by dividing the molecular mass by 13, because the molecular mass of carbon and hydrogen, when you add them up, they sum up to 13, that is 12 plus 1 is equal to 13. Now when a molecular mass M plus is known, a base formula can be generated which sums up basically the rule of 13, that is mathematically stating M by 13 is equal to N plus R divided by 13. Now the base formula will be CnHn plus R. The index of hydrogen deficiency of this particular molecule or double bond equivalence will be N minus R plus 2 whole brackets divided by 2. Now in order to understand this rule, let us consider this problem. Why don't we calculate the molecular formula of a compound with a molecular mass of 94 AMU, that is atomic mass units. You know that the molecular mass of this compound is 94. When you put it in the formula having the rule of 13, it comes up 94 divided by 13 is equal to 7 plus 3 upon 13. Now that gives you N is equal to 7 and R is equal to 3. Now the base formula is C7H10, that is CnHn plus R. So the index of hydrogen deficiency or DBE calculated is 7 minus 3 plus 2 divided by 2, which gives you 3. Now you can understand and you can make out how DBE3 will be able to tell you about the actual structure based on other information given. Special attention should be paid to DBE calculation because impossible DBEs like negative or fractional can lead to the rejection of one or more possible chemical formulas. Of course, the compound may contain other elements besides carbon and hydrogen. To account for other elements present, the appropriate number of carbons and hydrogens that equals the molar mass of the desired element is subtracted from the base formula to account for the added element or elements. Now table shows the carbon hydrogen equivalence for some or the more common elements that are involved in organic compound. Now you can see carbon or hydrogen equivalence for some of the more common elements found in organic compounds, and you can see what you have to subtract in order to obtain the correct element which is involved. Now let us take an example of benzamide which has a mass of 121, which is again odd. Applying the rule of 13 to benzamide results in the base formula of C9H13. Thus, if you calculate the DBE, it comes out to be 3.5. Since this formula has an impossible IHD or DBE, that is, degree of unsaturation cannot be fractional or negative, and the M plus is shown to have an odd mass, it is reasonable to add nitrogen to the formula. That is, you should now subtract a CH2, that is because nitrogen has a mass of 14, so CH2 should be subtracted, resulting in the new formula of C8H11N. Now the compound has a DBE of 4. Other possible formulas involving nitrogen and oxygen are C6H7N3 having a DBE of 5 and C7H7NO having a DBE of 5 again. Other spectral evidence, for instance IR and NMR data, can be very useful in identifying specific elements to include in this analysis. Now further analysis of the mass spectrum of benzamide, the accurate mass or the isotope ratio data is required to settle down with the correct formula. Benzamide has the formula C6H5CONH2 and the structure is shown to you in the figure. Now let us come to the most important concept in mass spectrometry, that is isotopes in mass spectrometry. A mass spectrometer separates and detects ions of slightly different masses and easily distinguishes different isotopes of a particular given element. Now this is the most distinguishing and important point of mass spectrometry. The molecular ions of 2-methylbutane have M by Z value of 72. The spectrum shows a very small peak at M by Z equal to 73. As you can see in figure, this peak is called M+1 because of the ion responsible for it is 1 unit heavier than the molecular ion. So the M+1 peak owes its presence to the fact that there are 2 naturally occurring isotopes of carbon, that is in the natural abundance of 98.89%, natural abundance of carbon 12 and 1.11% which is the natural abundance of 13C. So 1.11% of the molecular ions contain a 13C instead of 12C and therefore M+1 peak appears. Now this is clear from this figure of the mass spectrum of 2-methylbutane. Now students, peaks that are attributed to isotopes can help identify compounds which are responsible for the mass of that particular molecule. For example, if a compound contains 5 carbon atoms, the relative intensity of the M+1 ion should be 5, which has an abundance of 1.1%, is equal to 5, 0.011 multiplied by the relative intensity of the molecular ion. Now this means that the number of carbon atoms in a compound can be calculated if the relative intensities of both the M and the M+1 peaks are known. Now putting it in mathematical terms, number of carbon atoms is equal to relative intensity of M+1 peak divided by 0.011 multiplied by relative intensity of M peak. Now look at table which shows the isotopic distribution of several elements. Now you can see here the isotopic abundance of, which is the natural abundance of course, of carbon, hydrogen, nitrogen, oxygen, sulfur, fluorine, chlorine, bromine and iodine. Now special attention should be given to chlorine and bromine because as you can see the 35 chlorine has a natural abundance of 75% and the 37 chlorine has a natural abundance of approximately 24%. That means the peaks will be 1:3 in ratio in mass spectrum. However, in case of bromine you have 79 bromines isotopic abundance of 50% and 81 bromine also has an abundance of 49%. Thus, in the mass spectrum which will be obtained, you will have the 2 peaks in the ratio 1:1. Now from the isotopic distributions again if you see, we see why the M+1 peak can be used to determine the number of carbon atoms in a compound. It is because the contributions to the M+1 peak by isotopes of H, O and the halogens are very small or non-existent. Now this formula does not work as well in predicting the number of carbon atoms in a nitrogen containing compound because the natural abundance of 15 nitrogen is relatively high. Now the mass spectra can show M+2 peaks as a result of the contribution from 18 oxygen or from 2 heavy isotopes in the same molecule, that is 13C and 2H or deuterium or 2 13Cs. Most of the time the M+2 peak is very small. The presence of a large M+2 peak is evidence of a compound containing either chlorine or bromine, because each of these elements has a high percentage of naturally occurring isotopes, that is 2 units heavier than the most abundant isotope. This is majorly observed in compound containing bromine and chlorine. That is why we always say that it is important the halogens case. Now let us consider the mass spectrum of Br2, that is bromine. It contains 5 peaks and has a nearly 50-50 mixture of isotopes having atomic masses of 79 and 81 atomic mass units respectively. Thus, the bromine molecule may be composed of 2 bromine atoms, that is 79 bromine. So, the mass is 2 into 79 is equal to 158 AMU. 2 bromine 81 atoms, the mass will be 2 into 81 is equal to 162 AMU, or the more probable combination of 79 bromine and 81 bromine. So, the mass will be 160 AMU after adding 79 and 81. Now, fragmentation of bromine to a bromine cation then gives rise to equally sized peaks at 79 and 81 AMU. Now, you can see this in this figure what I have already stated. So, the mass spectrum of bromomethane contains 2 peaks of equal intensity 1:1 for CH379Br and CH381Br. This is clearly seen in this next figure. If the M and M+2 peaks are about the same height, then the compound contains 1 bromine atom, because the natural abundances of 79 bromine and 81 bromine are almost the same. Now, let us consider the case of vinyl chloride. The molecular ion consists of 2 peaks, M by Z is equal to 62 and 64 in 3:1 ratio, and M and M+2 ion. For the natural abundances of the isotopes of chlorine and bromine, one can conclude that if the M+2 peak is 1/3 the height of the molecular ion peak, then the compound definitely contains a chlorine atom, because the natural abundance of chlorine 37 is 1/3 to that of chlorine 35. Now consider the molecular ion in the case of methylene chloride, another chlorine containing compound, which has 3 peaks at M by Z 84, 86 and 88 AMU for M, M+2 and M+4 ions respectively. The intensity ratios of ions differing by 2 AMU indicates the presence of chlorine or bromine in a molecule or an ion. Now, the relative intensities of isotope peaks for bromine and chlorine combinations are shown in this table. Now, students, let us summarize this module. A mass spectrum is usually represented by a vertical graph with each bar representing an ion having a specific mass to charge ratio, that is M by Z, and the length of the bar indicates the relative abundance of the ion. The radical cation represented by M plus dot is called the molecular ion or the parent ion. The most abundant ion formed during ionization gives rise to the tallest peak on the mass spectrum, which is called the base peak. The ion appearing at an M by Z ratio that depends on its mass as well as the mass of the original ion from which it is formed is called metastable ion. The effect of nitrogen atoms on the mass of the molecular ion in a mass spectrum is called the nitrogen rule. A compound that contains an odd number of nitrogen atoms gives an odd molecular ion, whereas a compound that contains even number of nitrogen atoms gives a even molecular ion. Now comes the rule of 13 we stated. The rule of 13 is a useful method for determining the possible molecular formula of a compound from molecular mass. If the M and M plus 2 peaks are about the same height, then the compound contains one bromine atom because the natural abundances of 79 bromine and 81 bromine are about the same, that is 50-50%. From the natural abundance of two isotopes of chlorine and bromine, one can conclude that if the M plus 2 peak is 1/3 of the height of the molecular ion peak, then the compound contains definitely a 1 chlorine atom because the natural abundance of 37 chlorine is 1/3 that of 35 chlorine. Students, I hope you found this module very informative.